schemes also. What can we say about the number of valence electrons of metals? Usually, they contain small numbers of electrons, valence electrons, from 1 to 3. Atoms of nonmetals usually contain larger number of electrons, greater than 4, for example. So, how can be realized this octet rule for the atoms of metals and nonmetals? For metals, it is easier to release electrons because they have small number of electrons. You can see 1 electron only in a sodium atom. Atoms of nonmetals can accept small number of electrons. So to get 8 stable, 8 electronic configuration, you can see chlorine in outermost electron shell has 7 electrons and it gains 1 electron. In this way, sodium atom, now sodium ion already, has 8 electrons in its outermost electron shell, and chlorine atom has also 8 electrons. We can represent this reaction using Lewis electron dot diagram. Electrons are represented by dots. Or we can use electronic formulas to represent configuration of the atoms, electronic configuration of these atoms. Looking at this configuration, we can see that at the 3rd electron shell, sodium has a 3s atomic orbital, 1 electron. Chlorine has a 3p atomic orbital, 5 electrons. And after releasing electron by sodium atom, it has configuration 2s2, 2p6, 2nd electron shell, outermost electron shell, and there are 8 electrons. And for chlorine, the outermost shell, electron shell, is still 3rd electron shell, and now there are again 8 electrons. Another way to represent this formation of an ionic bond. At the first stage of this process, ions are formed, sodium plus, chlorine minus ions. At the second stage, there is electrostatic interaction, electrostatic attraction between oppositely charged ions. First, sodium donates electron and becomes sodium ion. This 11 means atomic number of sodium. Atomic number, I'd like to remember, shows the number of protons. Because the atoms are neutral species, it shows also the number of electrons in this atom. What is the meaning of this energy with E1, which has negative sign here? What is the name of this energy? I will look at the virtual room. Still no answer. Okay. There is, thank you. Ionization energy. So how can we define ionization energy? This is the energy needed to release one electron from atom in a ground state. So, to remove electron from one atom, we need to give this energy, E1. Next, chlorine accepts this electron, and second energy is released. What is the name of this energy? How can we name it? Electron affinity. So at the second process, energy is released according to the sign you can see. But the problem is that E1 is greater than E2, which means the energy needed for removing the electron is larger than the energy released. That's why we accept that the first stage, this is the first stage, formation of ions, and the second stage, interaction between these ions, proceed simultaneously. And this energy of electrostatic attraction, E, is enough to be used for formation of sodium cations. How can we characterize bond length when we have ionic bonding? So, suppose these ions, sodium and chloride ions, are far from each other. There is no energy, neither for attraction, neither repulsion. But when these two ions become closer each other, when they approach each other, the distance between these ions becomes shorter, and electrostatic forces between oppositely charged ions arise. Due to these electrostatic Columbus forces of attraction, energy of the system decreases. But when these two ions approach at a distance, which is given here, 236 picometers, after that point, repulsive forces arise. And if they are put closer, repulsive forces arise to a greater extent. What is the reason of repulsive forces? Well, the reason is the reason is repulsion between identically charged nucleus and electrons. So we can say the bond length of this ionic bond between sodium and chloride ions is 236 picometers. Compounds containing ionic bonds have specific characteristics, specific properties. Let us think about sodium chloride. We can say that usually these compounds are white, solid, brittle, crystalline compounds having high melting and boiling points. Usually such compounds are more soluble in polar solvents and water, and they are not soluble in non-polar solvents. Conductivity of these compounds is different in water solution and in molten state. These compounds conduct electricity, but in solid state they are not able to conduct electricity. Also, chemical reactions between ionic compounds are very fast, and their typical feature is they exist in very ordered state. They have crystal lattice, and here you can see such crystal lattices of sodium chloride. In lattice of sodium chloride, each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions. We will continue with second type of bonding, covalent bonding, and we will pay more attention of this bonding. We will start with the theory of Lewis about covalent bonding. In this theory, the basic term is share, because according to this theory, the bond between atoms is a result of sharing of electron pair between bonding atoms. For this electron pair, each atom contributes by 1 electron. For example, one hydrogen atom having 1 electron, second hydrogen atom having 1 electron, these 2 electrons are combined into an electron pair, and this electron pair is shared between 2 identical atoms, which can be represented by bond. Usually we show bonds in this way. In this example, this electron pair is equally shared between 2 hydrogen atoms. In such case, we say this bond is pure covalent bond or non-polar bond. Such non-polar bonds can be single, double, triple, depending on the number of electron pairs shared. Chlorine atom, second chlorine atom, chlorine molecule. So in this example, this electron pair is shared between 2 chlorine atoms. The other electron pairs are named lone electron pairs or not shared. Similarly, look at the atoms of oxygen. Each oxygen atom has two single electrons. And these two single electrons are combined so to produce two electron pairs, which are shared between these two atoms. And in that case, we say this is double bond. In the third example, two nitrogen atoms, each having three single electrons, are combined so to obtain nitrogen molecule in which molecule three electrons are shared. And this is triple bond. If we have bonding between different elements with different electronegativities, the bond, the covalent bond between such elements will be named polar bond because in such case the shared electron pair or pairs the sharing will be not equal. The most electronegative element will attract these electron pairs. Example of polar bonding. Hydrogen and chlorine. The electronegativity of chlorine is greater, and this is polar bond. This electron pair, the electron density of this shared electron pair is closer to more electronegative chlorine atom. Similarly, formation of molecule of water and bonding between oxygen and hydrogen atoms. Again, these bonds, oxygen, hydrogen, are polar bonds. I'd like to make a picture of sleeping students during my lecture. I won't do this. Okay. So, in a common model of Lewis covalent bond, each atom supplies one electron, like here. Chlorine, one electron, second chlorine atom, another electron, and electron pairs shared. But there is another type of covalent bonding, in which type of covalent bonding, which is named dative or coordinate bond, the atoms donates electron pair and the other atom accepts this electron pair, accommodates the electrons of this electron pair because the second atom contains free atomic orbital. Examples of such covalent bonding. Ammonia. Ammonia has lone electron pair at nitrogen atom. Proton has empty atomic orbital, which can accommodate this electron pair. And as a result of such interaction, ammonium cation is formed. Also, we talked previously when we discussed acids, bases, about hydronium ion. So, water molecule, 2 lone electron pairs at oxygen atom, and again proton, having empty atomic orbital, at which this lone electron pair can be accommodated. After formation of these dative bonds, such dative bonds are indistinguishable from the other common covalent bonds. So looking at this structure, we cannot say which one of these bonds arises in dative type or arises as coordinate bond. We'll take special attention of coordinative bonding, especially when we study coordination compounds. Lewis' theory of covalent bonding explains types of electron pairs, explain how the bonds are formed between similar or dissimilar atoms. But it was unable to explain the shape of molecules, which is important for the properties of compounds. Another model is applied to explain or to represent the shape of molecules, which is named valence shell electron pair repulsion model, in brief, VESPA model. So it is easy to characterize this the shape of molecules according to this model, depending on the number of electron pairs in a covalent bonded molecule. In case there are 2 electron pairs around central atom, like in this example, the shape is linear. In case around central atom there are 3 electron pairs, the shape is trigonal, planar. In case there are 4 electron pairs around central atom, the shape is tetrahedral. And maybe you remember this molecule of methane, which is shown here. Sometimes around the central atom are not 4, not 3, but 5 electron pairs. And in such case, the shape is trigonal bipyramidal, like in the molecule of phosphorus pentachloride. Or in case there are 6 electron pairs around the central atom, like in sulfur hexafluoride, the shape is octahedral. Obviously, we are going to discuss next theory about chemical bonding. That's why we need to mention some drawbacks, some disadvantages of Lewis and VESPA theories. First, this theory cannot explain deviations from the octet rule for molecules barium dichloride, boron trichloride. Around boron there are 6 electrons, not 8. phosphor and pentachloride. Around phosphorus there are 10 electrons, not 8. Or even in sulfur hexafluoride, around sulfur, there are 12 electrons, not 8. Lewis' theory couldn't explain existence of bond with one electron only. It is proved that such molecular species H2 plus exists. Also, this theory couldn't explain the paramagnetic properties of oxygen molecule. The next theory we will discuss is valence bond theory, which is developed by Hitler and London. This theory is developed on the basis of quantum mechanics. According to this theory, atomic orbitals of bonding atoms don't change during formation of chemical bonds. They don't change. They overlap. So the basic term here is overlap. What is the meaning of overlapping? The electron density of one atomic orbital enters the electron density of the second atomic orbitals. According to valence bond theory, you can see that covalent bond is formed by overlapping of half-filled atomic orbital. What is the meaning of half-filled? Having one electron only, with half-filled atomic orbital of the other atom. The electrons of these overlapping atomic orbitals should have opposite spin to arise bonding. And the larger is overlapping, the stronger is the bond. Again, the simplest molecule example. Formation of hydrogen molecule. Each hydrogen has one s electron. But to form hydrogen bond, these two electrons should have opposite spins, as it is shown. And you can see overlapping between these two atoms. The electron density between between nuclei of bonding atoms increases, and probably the interaction between positively charged nucleus and this raised electron density holds these two atoms together. This is simply to remember the atomic structure. Each atom has nucleus and electrons. In the nucleus, there are protons and neutrons. But we will deal with electrons because, I'll repeat, for chemistry, for chemical reactions are important electrons, especially electrons of the outermost electron shell. Different combination between these electrons results in formation of chemical bond. Different type of interaction arises between bonding atoms. And you can see if two bonding atoms are close each other, repulsion forces between identically charged nuclei arise, and repulsion forces between identically negatively charged electrons. But there are also attractive forces between electrons, negatively charged electrons, and positively charged nucleus. And the distance between nuclei of bonding atoms is named bond length. And again, we can represent the energy diagram of formation of chemical bond between two hydrogen atoms. When these two hydrogen atoms are far each other, no interaction between them, but when they start approaching closer each other, the energy of this system starts to have minimal values. Why? Because when they approach close each other, the electron density of one atom enters the electron density of the other atom, and in this way the electron density between bonding atoms, between their nuclei, increases, and the system, the energy, potential energy of such system decreases up to distance 74 picometers. After that, repulsion forces arise between identically charged species, nuclei or electrons. The energy of system increases. The moment at which these two energies, energy released when chemical bond is forming, and energy absorbed, energy needed to break this bond, this is bond length of this hydrogen molecule. And here I would like to remember how we represent electron configurations of different of the atoms of different elements, simply to show that there is number showing energy level, a type of orbital which can be, and this index here shows the number of electrons in this orbital. Electron configuration of carbon, for example, the element carbon is 1s2, 2s2, 2p2. At electron shell 1, there are 2 s electrons. At electron shell 2, there are 2 electrons at s atomic orbital and 2 electrons at p atomic orbitals. The electronic configuration of atoms, of the elements, can be represented by formulas. This is formula of the atom hydrogen, 1s1, and by orbital diagram. Helium 1s2 orbital diagram for helium, carbon orbital diagram for carbon, or nitrogen orbital diagram, or chlorine orbital diagram. Which of these two types of representing of electron configuration is more informative? Whether formula or orbital diagram? In my opinion, orbital diagrams, because using orbital diagrams, we can have electrons distributed not only in subshells, but at each atomic orbital. For example, here, for chlorine, the valence electron shell 3. The valence electron configuration 3s2 3p5. But the orbital diagram shows how these 5 electrons are distributed into 3p atomic orbitals. What happens? Again, something. Wait for a while. I will try to repair. Please wait. There is technical problem again, and still exists. I don't know why. I will try to repair. Yes. Okay. We can continue. Rules for creating of these orbital diagrams. There is a principle of Auerbach. According to this principle, first, lowest energy orbitals are occupied first. And you can see example. Which element configuration is this one? Looking at this configuration. Can you find? 1s2, 2s2. Element number 4, because there are 4 electrons. And as you can see, these first 2 electrons occupy 1s atomic orbitals. And it is impossible the next 2 electrons to occupy 2p atomic orbital, because 2p atomic orbitals are of higher energy than 2s atomic orbitals. So they should occupy 2s atomic orbital first, and after that, the next electrons will be able to occupy higher energy atomic orbitals. According to Pauli's exclusion principle, each atomic orbital can be occupied by maximum 2 electrons. And these 2 electrons should have opposite spin. So when we prepare orbital diagrams, this is wrong. 2 electrons at 1 atomic orbital should have opposite spin. There is also Hund's rule. According according to Hans' rule, electrons of equivalent atomic orbitals should be occupied first with single electrons of parallel spin, and after that, these electrons will be doubled. So this is wrong presentation of distribution of occupying atomic orbitals with electrons. This is correct. 2p atomic orbitals are occupied by 3 single electrons with parallel spin, and after that, the fourth electron can make such bond, electron pair. The shape of atomic orbitals. Different atomic orbitals possess different shapes. S-atomic orbital shape, p-atomic orbitals, and d-atomic orbitals. What can we say? The orientation of S-atomic orbitals is toward all directions in the space. The orientation of p-atomic orbitals is along axis X, Y, Z. The shape of these p-atomic orbitals, the shapes are similar. These p-atomic orbitals differ only in their direction in the space. They have the same shape and the same energy. That's why we say these 3p atomic orbitals are degenerate or also equivalent atomic orbitals. Similarly, we can describe the atomic orbitals. As you can see, the shape of the atomic orbitals is almost the same. Only one of these named DZ2 has different shape. The other have same shape, but their orientation in the space is different. So you will not be required to draw the atomic orbitals, but you have to understand their direction, the direction of their lobes. So you can see that the YZ atomic orbital, the lobes of the atomic orbitals lay in a plane determined by the axis Y and Z. The XZ, similarly, the lobes lay in a plane determined by the axis X and Y. The XY in a plane determined by the axis X, Y. And these lobes lay between axes. This atomic orbital, here cannot be seen, that's why I'll make smaller, is indicated as dx2, y2. The lobes of this atomic orbital lay along axes X and Y. X and Y. And DC2 atomic orbital, the lobe, this one, is orientated along Z axis. I'm saying now this because we will deal with the atomic orbitals when we discuss coordination compounds. Types of bonds, of covalent bonds. We will start with sigma bond. Now it's better, not completely better. Why? I'll increase. Okay. Sigma bond we have when the overlapping between atomic orbitals is end to end. And when we can say when the overlapping is along the line between bonding nuclei, between the nuclei of bonding atoms. Sigma bonds are single bonds. Sigma bonds, we can say, are localized bonds. Localized bond we have when we have bond between only two atoms. In case bonding is between more than two atoms, we will discuss this later. We will talk about delocalized bonding. So how can we represent overlapping between atomic orbitals, between different types of atomic orbitals? 2s atomic orbitals, like in hydrogen molecule. 2p atomic orbitals, end-to-end overlapping along the internuclear axis. S and p atomic orbital, again overlapping end-to-end. Sigma bond can be between p atomic orbital and d atomic orbital, between s atomic orbital and d atomic, or between two d atomic orbitals. So, sigma bond, in the formation of sigma bonds, all types of atomic orbitals can take part. Better pictures of bonding copied from internet. Sigma bond between two s atomic orbitals. Sigma bond between p and s atomic orbital, and sigma bond in the molecule of hydrogen fluoride between hydrogen and fluorine, or sigma bond in the molecule of fluorine between 2p atomic orbitals of fluorine. Pi bond. Depending on the way of overlapping, when overlapping is sideways or lateral, we say this is pi bond. You can see overlapping between 2p atomic orbitals. Sideways, between p and d atomic orbital, between two d atomic orbitals. So, overlapping occurs above and below the line between nuclei of bonding atoms, above and below this line or this plane. In the framework of valence bond theory, pi bond can be created only after formation of sigma bond. Example, molecule of oxygen. One oxygen atom having 2p atomic orbitals. This is not the atomic orbital, this is 1p and another p atomic orbital. These p atomic orbitals overlap end-to-end. End-to-end overlapping gives sigma bond. And these two orbitals overlap sideways. In this type of overlapping, like here it is shown, pi bond is formed. That's why we say in the oxygen molecule there is one sigma bond, and this is sigma bond, and one pi bond. The double bond consists of sigma and of pi bond. Molecule of nitrogen, similarly. There are 3p atomic orbitals of each nitrogen atom, which are directed toward X, Y, Z axis. By end-to-end overlapping, sigma bond is formed. And by sideways lateral overlapping, two pi bonds are formed. This is sigma bond. This is one pi bond between these two p atomic orbitals, and this is second pi bond. Overlapping at sigma bond is larger than overlapping when we have pi bond. That's why we say sigma, talk about this later, are stronger than pi bonds if we need to compare the strength of these bonds. Also, what is typical for pi bonds is that, for example, S atomic orbitals cannot take part in formation of such type of bonds. S orbitals are excluded from such type of bonding. Only P, D, F, etc. atomic orbitals can form pi bonds. What is typical for pi bonding is also that when we have such type of bonds, these bonds can participate in delocalized bonding. In such case, pi bonds is shared between more than two atoms. And again, we return to pure or non-covalent, non-polar covalent bond. Such bond, I already mentioned, is when we have two identical atoms, or when we have equal sharing the bonding electron pair between atoms. Examples are molecules of chlorine, fluorine, oxygen, nitrogen, hydrogen. So, polar covalent bond we have when the bonding is between different atoms having different electronegativities. And as a result of these different electronegativities, different non-equal sharing of bonding electron pair is the result. And in such a case, we say there are dipolar structure, or such molecules formed of two different atoms, two atoms having different electronegativities. These are named dipoles. Concrete example, molecule of hydrogen fluoride. So the electronegativity of fluorine is larger than the electronegativity of hydrogen. Two poles are formed in this molecule, partial negative charge, and at the other end, partial positive charge. And this is dipole molecule possessing dipole moment. Dipole moment, we use the Greek letter mu to indicate dipole moment, and the units for dipole moment is dpi. The dipole moment is equal to the distance between partial charges and the charge, the product of the distance and the charge. Water and ammonia this molecule contains polar bonds, because bond between oxygen and hydrogen is polar, and the dipole moment is directed toward more electronegative oxygen atom. Bonds between nitrogen and hydrogen is also polar. The sum of vector dipoles in molecule of water is not zero. It is calculated to be 1.85 dBi. The sum of vector dipoles in molecule of ammonia is 1.46 dBi. So these two molecules contain polar bonds, and the whole molecule is also polar. But in case we have carbon dioxide, this is structural formula of carbon dioxide. Bonds between carbon and oxygen are polar. Sigma bond is polar, and also pi bond is polar. And vector dipoles can be represented in this way, but the molecule as a whole is not polar, because you can see that these vector dipoles cancel out. So probably you could have a question to determine whether a given molecule is polar or non-polar. Because we already realized that having polar bonds in the molecule is not necessary, not enough, not the only condition for a molecule to be polar. This is structure of cis-1,2-dichloroethene. And this is structural formula of trans isomer of this compound, 1,2-dichloroethene. Look at dipole moments, because the bonds between carbon and chlorine are polar bonds. What can we say in such case? The isomers have different polarity of molecules. So, cis isomer possesses polar molecule because it possesses dipole moment. But trans isomer, in which opposite dipoles are cancelled, is not polar molecule. More examples of polar and non-polar molecules. Usually, symmetrical shape of molecule arises in non-polar molecules, and asymmetrical shape gives polar molecules. We already talked about carbon dioxide. In carbon dioxide, in carbon disulfide, the shape is symmetrical. The atoms around central atom are the same atoms. So carbon dioxide and carbon disulfide molecules are non-polar. Non-polar molecules are boron trifluoride. Same atoms symmetrically distributed around boron. Non-polar molecule is molecule of methane, symmetrically distributed for hydrogen atom around carbon atom. The bonds are polar, but the molecule is non-polar. Non-polar is the molecule of carbon tetrachloride also. You can see polar bonds, the direction of dipoles is different than if we compare dipoles with in methane. But as a whole, the molecule of carbon tetrachloride is non-polar. Non-polar is also the molecule of sulfur trioxide. And when we have asymmetrical molecule, several examples, such molecules having polar bonds are also polar molecules. Example, water. The compound of fluorine with oxygen, we cannot say oxygen fluoride, or we can say oxygen fluoride, not oxide of fluorine, because fluorine is more electronegative than oxygen. Polar molecule is the molecule of sulfur dioxide, non-symmetrical shape, hydrogen sulfide, ammonia, nitrogen trifluoride, phosphorus trichloride. And to complete this, next examples. When we have, in these examples, this slide, we have non-polar molecule of sulfur trioxide. It is non-polar because there are 3 oxygen atoms. But in case these atoms are different, in case we have again symmetrical shape, but different atoms, this means that in such case, the polarity, the molecule will be polar. Non-polar molecule of, we already discussed, methane, carbon tetrachloride. But if we replace one or more than atoms here with another atoms, we obtain polar molecules. I think we can stop here and we will continue with characteristics of covalent bonds next week. Have a good day. Goodbye. Bye.